Okay, good afternoon. Thanks for coming to this talk. My name is YongTang. I'm a maintainer and the CIO lead of Tensorflow project. This is my GitHub handle. By the way, if anyone wants to reach me or have any questions, you can always ask me or ping me at GitHub, and I should be available most of the time. Okay, in today's talk, my focus is going to be on real-time streaming data with machine learning. Specifically, I'm going to discuss about the integration of Tensorflow and Apache Kafka and see how we could combine those two frameworks and build a real-time streaming data pipeline with machine learning functionalities. Oh, need volume further? Oh, okay. We deal with real-time streaming data every day. We have data collected from IoT sensors. We have data from GPS position updates. We have web transactions, and we also have a social media update. For those real-time streaming data, they typically are generated in continuous fashion and in very large volumes. In real-world experience, when we process those real-time streaming data, typically they are placed under architecture of so-called event-driven microservices architecture. For event-driven microservices, essentially you have a streaming framework at the central place. The streaming framework could be Apache Kafka, but it could also be services provided by cloud vendors such as AWS Kinesis or Google Cloud pops up. The data collected from different endpoints, such as from APIs, from applications, or from devices, collected and delivered to Apache Kafka first. On the other side, you have different services, typically written in like Java or Golang or some other language, and they pick up the data from Apache Kafka first. They do the data transformation, they do the data processing, and eventually they get the result and they write the data back into Apache Kafka. And the next service will pick up the data again from Kafka to continue processing. We discussed about event-driven microservices, but for this talk, our focus is on real-time streaming data with machine learning. So what we really want is to replace those application services by machine learning tasks, like this way. So if we can have services running by like a TensorFlow or like a PyTorch, and if we can read the data from Apache Kafka, do the machine learning task like for training or inference, and then send the data back to Kafka, then that's the way we want to achieve for event-driven microservices with machine learning. We mentioned TensorFlow, so I guess people in this room already heard of TensorFlow before. TensorFlow is one of the most popular machine learning frameworks. It was originally developed by Google and open source in 2015. Since then, we have seen explosive growth of TensorFlow, both in machine learning and open source community. At the moment, the most stable version of TensorFlow is 1.13. However, TensorFlow 2.0 will be released pretty soon, likely in several months, and there are a lot of change in TensorFlow 2.0. So I'm going to just briefly introduce some of the background in TensorFlow 2.0 and see what kind of change that has been introduced and how this could impact the real-time streaming data pipeline. So in TensorFlow 2.0, the biggest change is the model building. Before 2.0, you used to have many ways of build models. You could use TF.keras, you could use TF estimator, you could use TF layers, or you could also use TF slim. People have been talking about that, say you have 4 or 5 ways of doing the same thing. So fortunately, in TensorFlow 2.0, everything has been consolidated, and TF.keras is a recommended API. This is actually a good thing because the TF.keras has a very easy, simple, and succinct API. Allows the user to build models very quickly. Another major change in TensorFlow 2.0 is eager execution. We all know in the past, TensorFlow has a concept of static graphs. For static graphs, you need to lay out the whole graph and then let the graph to run and wait for the graph to complete to get the result. The static graph has an advantage in that you can easily redeploy in production environment and reliably do that. The disadvantage for static graph is that if you want to debug or you want to do development, it's very hard because even if you just make a small change in the graph, you still have to wait until the whole graph runs and complete to get the result. So debug has been a painful process. Fortunately, in 2.0, eager execution has been enabled by default, so you should be able to run TensorFlow imperatively, and it's just like running a Python program. So that's a good thing. Another major change in TensorFlow 2.0 is tf.data. tf.data is essentially the data processing pipeline of TensorFlow. It allows you to efficiently process the data and do training and inference. It is already part of pipeline, so that actually helps make everything very simple for 2.0, and hopefully that's going to be beginner friendly for 2.0 as well. To give an example of what 2.0's code base looks like, this is an example to do a training of a neural network based on MNIST dataset. So the first several lines, the first line essentially read the data from MNIST dataset. The second line is the data pre-processing. We want to do data pre-processing to convert the image type from a byte to a floating point so that it could be possible to be fed into Keras model. And then we have a heavy lifting of Keras model building and model compile. Once the model has been built and compiled, everything should be ready. The next step, if you want to do training, you can just call model.fit. And if you want to do the inference, you can call model.predict. And that should be all you need to complete a machine learning task. So as you can see, it's massively simplified in TensorFlow 2.0. For us, for this talk, the focus is going to be on the first piece, the data reading and data processing, because we want to focus on building a real-time streaming data pipeline with machine learning. So we also talk about the integration of Apache Kafka. So essentially, the idea is there a way to replace the data reading and the data pre-processing by something like a Kafka connector, such that we can read the data from Apache Kafka directly, instead of like this code base to read the data from a file. So that's our focus. Before we talk about Apache Kafka and the KafkaDataset, I want to mention about the motivation of having a data pipeline in machine learning. So why do we need a data pipeline at the first place? There are several reasons to have a data pipeline in machine learning, and the biggest reason is a performance considerations. We all know machine learning need to use lots of resources. You need to access I/O, need to access CPU, and also need to access GPU. And GPU is the most expensive one. That actually means the utilization of I/O, CPU, and GPU could be issue, because if your machine learning task is waiting for the I/O to complete all the time, then likely you're going to waste a lot of resource on GPU. And then we all know GPU is the most expensive ones. You want to make sure your investment are getting back. This is a diagram shows you the basic idea of why data pipeline is important. At the top, you see there's essentially no data pipeline. You read data from I/O. The I/O could be disk I/O or could be from network. You wait until all the data coming in. You do the pre-processing or do some operation that's suitable for CPU. And then you do the operation on GPU. I think we could see most of the time your GPU is idle. And that's very, very important, because that actually means your performance might be down. Because your most powerful piece, the GPU, is not fully utilized. On the bottom one, you see we have a data pipeline. We want to make sure the I/O is running, while at the same time the GPU could be started working as soon as the data is available. With that, we see a increased utilization of GPU, and that should drastically improve the performance. By the way, in tf.data, the whole pipeline has already been optimized, so you shouldn't worry too much about the data pipeline. Another motivation for data pipeline is flexibility. We deal with different kind of data, and the data have different formats. We want to make sure we can support a variety of data format across the board. So that's a flexibility we should be concerned as well. For data format flexibility, tf.data is not very good with data format. If you look at the supported format, at the moment, out of box, TensorFlow only supports 3 types of formats. The text line dataset essentially just gives you the ability to read a text file. The fixed length record dataset essentially allows you to read a file if each record is a fixed length. That's very limited. And the default format TensorFlow support is TFRecord. By the way, anyone heard of TFRecord before in this room? Okay, it's not surprising that only one gentleman heard of TFRecord before. So the TFRecord essentially is just a sequence of binary strings. You could consider TFRecord as a protocol buffer for serialization and deserialization. The usage of protocol buffer is understandable because protocol buffer is also developed by Google. If you look at the TFRecord itself, it's actually very flexible and simple because it can adapt it to allow you to have any format and any data structure as long as you like. So what's the issue with TFRecord? The only issue with TFRecord is that, first of all, it's only used by TensorFlow. I mean, almost no one heard of TFRecord before in this room. And secondly, and more importantly, there's no ecosystem support for TFRecord outside of TensorFlow. So this is very important because when we try to use a data format, we are not just use a data format because one metric number is good, or maybe because there's a performance benchmark. We all know performance benchmark could be biased, but we are not picking up a data format for certain performance benchmarks as well. One of the biggest reasons we select one format versus another is to have a very rich ecosystem support such that we can use different tools to meet our requirement and to make our life easier. For example, in big data, if people are familiar with big data, people know Apache Packet used widely in big data. So the reason to use Apache Packet is that we have very rich ecosystem support. In one of the company I worked for before, we used to save all of our big data in Packet format and save that on AWS 3. The reason we do that is we can use different tools. We can write Spark jobs. Our Spark job could run on AWS EMR. We also could use even run SQL queries with AWS Athena. So with the Packet format, it give us a very rich tools to do all kinds of things and fit different departments, different organizations. But with TFRecord, of course, that's not possible. You cannot run Spark jobs anymore. You can also not run SQL queries on top of TFRecord as well. And even worse, here we are talking about the integration of Kafka. So how are you going to read data if TensorFlow only support TFRecord? If you look into the internet or search for the solutions with Google, you probably find some of solutions proposed by different parties over the internet. Some of solutions are so-called infrastructure solutions. For those type of solutions, essentially, people try to introduce additional component to support the missing piece. For example, we know Kafka has nothing to do with TFRecord, so people say, yes, we could launch a process to do the conversion. We have process read data from Apache Kafka, converts the data into TFRecord. Because TFRecord is a file, so we are going to save that in a persistent storage or file system, or maybe distributed file system. And now we can launch our TensorFlow tasks, read the data from TFRecord, do the processing, do the training and the inference, and they write the result back as a TFRecord. Another process obviously could read the TFRecord from disks and then write the message back into Apache Kafka. It sort of works, but as we can see, it's very complicated. The reason it's complicated is that we introduce many infrastructure components, and for every component, it comes up with maintenance costs. Because we need to have additional DevOps, we need to have additional SREs, infrastructure engineers, to make sure every component is up and running all the time. We also need to have logging and monitoring solutions to cover those additional components to make sure it's up all the time. So people has been raising a question about, is there a simple way to address the need? Because all we need is to read data from Apache Kafka, right? And once the data is imported into TensorFlow's graph, either a static graph or with eager execution, once it's in the graph, TensorFlow itself already have a very rich kernel ops to allow you to do all kinds of transformation and all kinds of tasks. So you should be fine as long as it's in the graph. So here you go. We introduce, we actually implement the KafkaDataset in TensorFlow. To introduce some further background, KafkaDataset has already been implemented in TensorFlow in 1.x package. It's in the format of tf.contrib, but if you install TensorFlow by default, like a pip install TensorFlow, it's already there. In 2.0, we made some additional change because we want to modularize TensorFlow. So some of the I/O components spin off to have a separate package called TensorFlow-IO, which is managed and maintained by the special interest group of I/O for TensorFlow. To install that, it's also very easy. In Python, you only need to have a pip install TensorFlow-IO, and you are ready to go. We talk about reading data from Kafka to TensorFlow. So that's a read. We also have a support of write data back into from TensorFlow back into Kafka. So that's the write operation. So with the read and write operations, you should have all the tools necessary to build a real-time streaming pipeline with TensorFlow and Apache Kafka. So this is the same code base we mentioned before. We do the training and the inference with MNIST dataset. That's a piece we want to replace. So of course, we can do that already with Kafka dataset. So if you take a look, data reading is as simple as just one line. So you read data into train dataset, and that you should be ready to go. And you can do all the operations to do the pre-processing. I skipped the pre-processing because in Kafka essentially, it's actually deliver you as a stream. So you still need to do one additional decoding. But this one should be fairly straightforward depending on your format. For example, if your message is just an image file, on the data pre-processing part, all you need to do is just have a calling a TensorFlow kernel ops of, let's say, decode JPEG, and that's all. So as you could see, the rest of the components remain the same. We haven't touched anything, and you could already do the training, and you can apply the model you have built before and do the same thing. So that's actually a very easy thing to work. And then we talk about the inference. Inference, it also means we want to write the data from TensorFlow back into Kafka. And the thing is, we want to write the data in continuous fashion. So if the data is coming in let's say, in batches, every batch, at the end of every batch, we want to make sure we can just invoke that. We don't want to wait until everything has been complete to write the data back. By default, tf.keras model predict function will return the result once everything has been completed. So you cannot directly calling that. So what we could do is to hook up the callback. In tf.keras callback, there is a hook point of unpredict batchend. As you could see this line. At the end of each batch, the tf.keras callback give you the data you need for partial result. In this way, you can just write the data back into Kafka, and that's all you need. As you can see, it's slightly more lines of code you need to work on, but it's still massively simplified. And with model.predict plus callback, you could really build a pipeline with data continuously coming into your TensorFlow graph, and you continuously rendering the prediction back into Kafka, and that should help you to build a really cool pipeline. So now with KafkaDataset, we massively simplify the infrastructure. We could just launch TensorFlow services, and all you need to do is just calling the KafkaDataset to input the data and export data back into Apache Kafka. That give you all the tools available for building a data pipeline, a real-time streaming data pipeline with TensorFlow. Okay, one final piece about the TensorFlow I/O package itself. We mentioned about the SIG-IO. SIG-IO is a special interest group of TensorFlow. Before the launch of 2.0, we decided that we want to modularize, so a collection of I/O-related operation has been grouped, and spin off as a special interest group is still under TensorFlow organization, and we have very tight integration with TensorFlow itself. The SIG-IO itself has a focus. By the way, we have several special interest groups. SIG-IO is one of them, and it has a focus on input-output. It has focus on streaming and data format. In this talk, our focus is on Apache Kafka, but we also have support on different streaming frameworks like AWS Kinesis and Google Cloud PubSub. Those are services provided by cloud vendors. In addition to streaming data support, we also have support for different serialization and deserialization. We have support for Apache Packet and Apache Arrow, which has been used widely in big data community. Apache Ignite is a memory-centric caching solution, allows you to speed up. And finally, we have persistent storage support, so that if you have file saved in AWS 3 or Google Cloud GCS, you don't need to download the file. You can just point in the file directly, and you should be able to read that directly. So I think that's pretty much it for today's talk. So I'm just wondering, any questions?